How's it going today, everybody? Our last video covered aqueous substances and molarity, so today we're going to look at the other measurement of dissolved substances, molality. Our goals for today are to learn about what molality is and why it is used, to do a bit of practice calculating molality and using molality in calculations, and then to compare and contrast molality and molarity. Molality measures concentrations of solutes dissolved in a solution, just like molarity does, but it does so in a very different way. Molality measures moles of solute per kilogram of solvent. Now, in the last video, I made a point of emphasizing that molarity measured moles of solute per liter of solution. This allowed us to measure the solution as is, then simply convert using the molarity. Molality, unfortunately, requires us to know the mass of our solvent separate from the dissolved substances. This makes molality much less usable in the real world, but it is crucial when it comes to lab work. We'll discuss the reasons for this in a bit, but for now, let's look at how to use molality in conversions. The units of molality are moles of solute per kilogram of solvent. So the first problem says that 2 moles of copper chloride are dissolved in 3 kilograms of water. What is the molality of the copper chloride solution? So remember that the units for molality are moles of solute, so in this case that'll be copper chloride, per kilogram of solvent, which in this case is water. We have 2 moles of CuCl2 in 3 kilograms of water. So we could say that our molarity is 2/3, or molality is 2/3, sorry. That's why it's important to keep the two separate. But we're going to actually separate this so that there's a 1 on the bottom, and that will leave us with about 0.67 moles of CuCl2 per 1 kilogram of water. And that's going to be our molality right there. The second one asks how many moles of sodium hydroxide, NaOH, are present in a 2 molality solution with a 3.5 kilograms of solvent. So it's a little bit tough to find the wording of that, but this is the molality. This is how much solvent you have. So you have 3.5 kilograms of solvent. Kilograms of your solvent. And your molality is 2 moles NaOH per 1 kilogram of solvent. These kilograms of solvent will cancel out, and you will just end up with 7 moles of sodium hydroxide. So the calculations aren't too terribly difficult. The main issue with molality really is just that you need to have this solvent, which is whatever your particles are going to be dissolved in. You have to have the solvent separate from the moles of your solute, so whatever you're actually dissolving. And that can be really tricky because it's much easier to just measure a solution in volume and then worry about separating the two elements afterwards. Now let's compare molality and molarity. Molarity has the benefit of not needing to know much about the solvent separate from the aqueous substances, which makes it much easier to experimentally determine. Molality requires us to know the mass of the solvent by itself, which can be an issue. I said earlier that molality was important in lab use, and this is because it is more precise than molarity. If you remember back in the lecture on liquids and density, I said that liquids, like gases, can change volume based on temperature and pressure. This would make molarity change as well, as the number of moles of solute would not change, but the volume of the solution would. Molality, however, does not change in response to temperature and pressure, as both moles of solute and mass of solvent are constant. This means that molality is very precise and accurate under any conditions, while molarity can be more tricky. It is worth noting the difference in the way that each is written as well. We last time said that molarity was written as a number followed by a capital M. Molality is written as a number followed by a lowercase m. Although we will be mostly using molarity in the rest of the unit, do pay attention to the units just in case. Let's review. Despite the fact that we will mostly be using molarity moving forward, it is worth your time to understand that molality is used when precision and accuracy are important, most commonly in a lab setting. This is because the volume can change based on temperature and pressure, while the mass cannot. Otherwise, molality will mostly be forgotten in favor of molarity, but do pay attention to units moving forward just in case. Speaking of moving forward, next week we'll start looking at why any of this conversion nonsense actually matters, so make sure you're ready. That's it for today, and I'll see you next time.